recording here. There we are. How have things been going so far for the first 8 chapters? Has it been okay? Not too bad?
Yeah, I mean, it hasn't been really hard or
Okay.
anything like that. So
Okay.
yeah.
All right. Um, again, if you've got any questions at any point, just let me know. Yeah, I'm always out there, but everybody seems to have been at least pretty good about some level of communication here, so that's pretty good. I don't see much going on out on the
The
Muddy's Point links to suggest that there's a real sticking point on things. So that's there sort of as a monitor, as a guide to make sure that I can catch something at the very least. If something's going on. So tonight we're going to go over chapter 9. We're going to start talking about rotational motion. And rotational motion is a way we've already discussed up to this point, trying to describe linear motion, so motion in lines. And, what all information can we gather if something is moving in a straight line? How do we describe it? That's where we've come up with things. We've come up with the kinematic equations. We've come up with force. We've discussed energy of different types and things like that. And because of that, we have a pretty good model for how all of that particular type of motion works. And so now we're going to make a twist on things. And we're going to try to take a lot of those same concepts and we're going to apply them to motion with angles. And that's where this section really comes in and starts to describe motion in an angular sense. So that's going to be the focus here. And then going forward from here, we're going to cover several chapters here that are going to discuss other concepts, not just motion, but force, things like moment of inertia and linear or angular momentum and things like that. So we're going to see the rotation analogs of a lot of linear concepts that we've seen up to this point. So if you have a good focus on what's going on in a straight line, then as we start to turn things, we'll begin to see some parallels here. At least I hope so. So we're going to go ahead and start here with section 9.1, and where we discuss angular velocity and angular acceleration. So what we're going to have is, for an example here, is a bicycle tire. And we're going to put an axis that goes through the point of origin here. And so you can see the x-axis, you can see the y-axis, and we're going to mark, with chalk or whatever, a point at which we're starting the rotation. And then we're going to mark another point here at which we stop the rotation. So when we have situations like that, we're going to describe it not using an x or y coordinate system, but we're going to use it using a particular angle, and it's going to be called theta. And this angle is going to be measured as if we had the x-axis here, and we're going to see exactly what sort of an angle this thing rotates through. So this thing is already set here at a particular angle. And this really doesn't describe it too well, but I think here at time t1, if you can read that, you're going to have an angle here, and it's going to be theta 1. As it rotates through, it's going to create a second angle, or at theta 2. And the difference that you are going to see here is going to be called delta theta, or basically the change in the angle. And how we represent that with this symbol here, delta theta, we're going to take that, and just like we did with linear motion with the change in x or change in y, depending on what direction we're going through, we're going to take that change and we're going to divide it by the change in time. And when we do that, we're going to get a change of the position with respect to time. And if you remember back from previous chapters, that change in position with change in time is going to be defined as velocity. Well, when it comes to moving with angles, we are going to describe that as the change in theta over the change in time. And we're going to label that with a special letter, and it's going to be called omega. And omega is going to be the limit as delta t approaches 0 of the change in theta over the change in time. So this is going to be your average angular velocity. Now, if the angular velocity changes by an amount, which we're going to try to model here, it's moving with a certain angular velocity at this time, and then you can see here it starts to speed up because you have more axle spokes. At time 2, you can see that it's moving faster. You've got a change in angular velocity. That change in angular velocity with respect to time is going to give you the angular acceleration. So just like we did before with the change in velocity over the change in time being the acceleration, this is going to be the angular acceleration. And that is going to be how we're going to describe velocity and acceleration. So let's take a look here at this particular section. Okay. So in general, as I've talked about, you've got this really obnoxious oblong object here, and you've got an axis of rotation here, and you've got an angle, and it's made with a positive axis, rotates through this way, and the axis of rotation, of course, here is going to point out of the page. So how is theta going to be measured? It's going to be measured in radians, where you've got this arc length here, and that arc length divided by r is going to end up being your angle. Now, obviously, you can take that and change it around and solve for your arc length. And if you remember, and you may not, when s is equal to r, that is going to be 1 radian. In other words, you have an arc length that is going to be the same as the radius length. That is the definition of a radian. Now, when it comes to arc length, or the angle here, we're going to measure that in radians. So that's something to remember. So if you need to change from degrees to radians, then you've got this formula here that you can go through, where 1 radian is going to be equal to 360 degrees divided by 2 pi. That's basically, it's like a conversion from one unit to the next. And as it turns out, 1 radian is going to be about 57.3 degrees. So here's our discussion again regarding angular velocity, the average angular velocity. And again, you're looking at the change in the angle regarding over the change in time, and your units are going to be radians per second. The angular displacement must be expressed in radians. By convention, counterclockwise rotation has a positive angular velocity, and clockwise rotation has a negative angular velocity. The instantaneous angular velocity is going to be when delta t approaches 0. So an important point here is that because the body is rigid, all lines in it rotate through the same angle in the same time. It's rigid, so everything's moving along at the same time. So at any given instant, every part of a rigid body has the same angular velocity. So if an angle is measured in radians, the unit of angular velocity is 1 radian per second. Other units, such as revolutions per minute, can also be used. And the reason that sometimes those are used is not necessarily to make physics problems more complicated for the physics student, but actually you might be able to count when something has certain revolutions per minute, and then you can take that and rewrite it into radians per second, or whatever other time unit you want to use. So let's take a look here. Our merry-go-round, if any of those out there still exist. You've got a boy and a girl that are riding on a merry-go-round, so you can see them here. The boy is at the outer edge. The girl is near the axis of rotation. How do their angular velocities compare? So does the boy have a greater angular velocity? Does the girl, or do they have the same? So an object's angular velocity as opposed to its straight line velocity is going to be determined by the change in the angle of a line drawn from the axis of rotation to the object during any given unit of time. So both children have fixed positions on the same rotating object. They rotate through the same angle in the same time interval. Their angular velocity is the same as that of the merry-go-round. So the correct answer is going to be C. And that may seem a little counterintuitive there, but that's pretty much the way it goes. So angular average acceleration is going to be defined as the change in the angular velocity divided by the change in time. Its units, rather than length per second squared, like meters per second squared or something like that, this is going to be radians per second squared. The sign of this is going to depend on the rotation. If it's counterclockwise, then it's going to be a positive angular velocity. If it's clockwise, it's going to be negative. And again, the instantaneous angular acceleration is going to be represented with this formula. So let's go ahead and let's kind of work through one of these problems here. We're going to use the angular acceleration of a CD. To play music, the CD must rotate at high speed while a laser reads data encoded in a spiral pattern on the disc. So the disc has a radius of 6 centimeters, or if you convert that to meters, it's going to look like that. When data is being read, it's going to spin at 7,200 revolutions per minute, which, if that's actually close to the way it is, that's a lot faster than I would have given it credit for. So what is the CD's angular velocity in radians per second? And then how much time is required for it to rotate through 90 degrees? And if it starts from rest and reaches a speed, full speed in 4 seconds, what is its average angular acceleration? So here we are. We're drawing this out. We've got our CD. So we need to be careful to be consistent with the units. So we're going to use radians, meters, and seconds. So we've got meters here for the radius. We have a change in the angle here of 90 degrees. And we have angular velocity here at full speed of 7,200 revolutions per minute. So to convert the disk's angular velocity to radians per second, we're going to multiply this by 1 minute over 60 seconds, so that'll change it to revolutions per second. We're also going to change this from revolutions to radians. So we do 2 pi radians for every revolution. So we go through and we multiply all that through, all of those conversion factors. And this thing completes 754 radians per second of angular velocity. So from that definition, we're going to find the time delta t that it takes for the disk to turn through 90 degrees. So basically we take the delta t, put it over here, take the omega, put it under there. We know what the change in the angle is because that's going to be pi over 2 radians, because that's the 90. If we were to go a full 180 degrees, that would be pi, but if we just go half of that, then we end up at 90 degrees. So that's there. We know how fast it's going at that point. It takes 2.1 milliseconds to turn 90 degrees. So if the disk reaches final angular velocity of this in 4 seconds, the average angular acceleration is going to be this, 189 radians per second squared. So this is kind of interesting. A typical circular saw used in woodworking shops runs at 3,600 revolutions per minute. And it reaches full speed about 1 second after it's turned on. So the radius of a typical blade is going to be 12 centimeters. Note that the radius is not needed to determine the angular acceleration calculation. So anyway, kind of interesting stuff. All right, so moving on, section 2. When a body rotates with constant angular acceleration, then the angular position, velocity, and acceleration are related by these equations. You may notice how similar they look to the kinematic equations that we have for linear motion. And they are indeed quite similar. We're replacing a lot of velocity with angular velocity, replacing the linear acceleration with the angular acceleration, and replacing the position with theta. So you should notice a lot of parallels there. So that's going to be a lot of section 9.2, and in section 9.2, there will be a number of problems to work. These are going to be very, very similar to the types of things that you've already done. You can see all of the derivations going through here. Not really that interested in knowing, for you knowing how to derive them, but they are there, and it's not to say that they're not important. But you can kind of see here the connection between the two, and sometimes that can help. So let's say we have a spinning wheel, or a wheel is rotating with angular speed of omega naught. It also has an angular acceleration of magnitude alpha. So for which one of the following cases will the wheel eventually come to a momentary rest? Is it when the initial angular velocity is greater than 0 and the acceleration is greater than 0? Is it when the angular velocity is less than 0 and the angular acceleration is less than 0? Or is it when your initial velocity is greater than 0 and your angular acceleration is less than 0? Eventually, you're going to want, in order for it to stop, the angular velocity has to be 0. If its initial angular velocity and angular acceleration are of opposite signs. If this is true, then the wheel will momentarily come to a rest at this particular point in time, which is just a rearrangement of what you've got here. And then for t to be positive, either this or this must be negative, but they both can't be negative. So by process of elimination, you come up with C. So, and then you have several, or one other problem here that you can kind of work through. It's already worked out for you. All right, so we've got a relationship here between linear and angular quantities, again, in section 9.3. So we've got a particle in a rotating rigid body at a distance r from the axis of rotation, has a tangential speed given by this. The particle's acceleration has a tangential component and a radial component. So how does all of this fit in? Well, here's the picture of what's going on. You've got this particle on whatever this is, and it's moving around as the body is rotating around this particular axis. You have a linear acceleration in this direction. You have, or linear velocity in this direction, I should say. You have linear acceleration going on here at this particular point. This vector is comprised of a tangential acceleration and a radial acceleration. So where do these formulas come from? Well, we've been able to describe the velocity. The angular velocity here is v over r. So if you rearrange that, then the linear velocity comes to be this. Therefore, the radial acceleration, not the radial acceleration, but the tangential acceleration is going to be r times alpha. And then if you are interested in the radial acceleration, this is going to be, if you remember back with uniform circular motion, we had the radial acceleration as being v squared over r. In this particular case, in rotation, we're going to be looking at radial acceleration of omega squared times r. So if you take this and replace it in here, if you remember v squared over r, you replace it here, and this is what you come up with. In this particular section, there are going to be a lot of derivations and whatnot to try to get you to that point. Primarily, if you can just remember what those final formulas are, that's really kind of the key thing here that I'm wanting you to look at. So you can see here, you've got the rotation, you've got a point here, you know the relationship between the arc length and the radius, and then you've got what the velocity is headed off in this direction, and basically that comes from taking what would be the time derivative. We're not using calculus, but that's essentially where it comes from in order to get this particular equation. You're looking at the change of this over time and then the change of this over time. Since the radius doesn't change, then this relationship comes about. And that's what they're trying to hammer home here with this particular note. Speed of a point on a rotating body, this is pretty much what we are talking about here. Again, the radius is defined as the distance between the axis of rotation and this point. So let's proportional reasoning for a rotating disk. So we've got a rotating disk about an axis perpendicular to its plane. We've got point B on the disk, and that's going to be 3 times farther from the axis than point A. If the speed of point A is b, then what is the speed of point A? So speed in this case is going to be the magnitude of the linear velocity, not the magnitude of the angular velocity. Because this disk is a rigid object, all points on the disk rotate with the same angular velocity. In other words, they're going to cut the same angle at the same amount of time. The speed of a point is directly proportional to its distance, r, from the axis of rotation. Since point A is going to be 1/3 the distance from the axis than point B is, then the speed is going to be cut by 1/3. So the correct answer here is going to be B. And that's just using basic analysis here with that particular formula. Again, here we see the relationships with acceleration. Primarily, it's this formula as well as this one that I'm wanting you to remember. So let's say we have, we'll do another problem here. We've got a disk that spins with increasing angular velocity. Point B on the disk is twice as far from the axis of rotation as point A, so which of the following statements is or are correct? We'll take a look here at those, but let's go through the solution and let's figure out what we need to know here. The disk's angular velocity is increasing because that's what it's telling us. So the disk has angular acceleration. Well, that makes sense. It's getting faster, so the angle is accelerating. All points on the disk rotate through the same angle in a given time interval and thus have the same angular velocity and angular acceleration. So if they have the same angular velocity and same angular acceleration, then we have to rule out A, but C is in fact true because that's what it's saying here. A and B have the same angular acceleration. The radial acceleration on each point is going to be given by this. So point B is farther from the axis than point A, so the radial acceleration is going to be greater than that of A. And so in other words, B is going to have greater angular acceleration. And answers B and D are therefore incorrect. So the only answer out of this is going to be C. It's going to take some work to kind of go through that and kind of see this. And got a few problems here you can kind of go through. Kind of check that out. So now, kinetic energy, rotation, and moment of inertia. So, moment of inertia of a body with respect to a given axis is going to be defined by this. And I'm sure that makes perfect sense on the first reading and you don't have any questions about it. If you do, then you're smarter than I am, because when I went through physics, I never really got the idea of a moment, much less a moment of inertia. A moment is sort of a way of categorizing a larger body and how we can model a concept of mass. If it's a point mass, it really doesn't need a lot. But if it's a larger sort of oblong, strange type of shape, that gets to be a little bit more difficult. So if you are able to have discrete values, then you can go through and you can use this particular formula on each one of those discrete values. A lot of times you're going to have a solid object, and so it's going to be more complex than that. But R sub A is going to be the distance of mass element M sub A from the axis of rotation. And then you get the idea for M sub B and M sub C. Now, if you want to find the kinetic energy of a rigid body rotating around a stationary axis, you're going to use this particular formula. Once you figure out what this guy is, and if you know how fast it's rotating angularly, then you can determine the kinetic energy for the rigid rotating body. Also, in a uniform gravitational field, the gravitational potential energy of a rigid body with center of mass at a distance y sub cm above a reference level, where usually you set that equal to 0, the potential energy is set equal to 0, then U is going to be equal to mg y sub cm. So let's take a look at that. Okay, so here we have a discussion of kinetic energy for something that's moving in a straight line. If we take that straight line motion and we change it around to a rotational, this is what it ends up being. And then if we take the body and we divide it into its mass pieces, then you can see the derivation there. Because of that, we just take all of this junk right here. And we're interested in, rather than just trying to figure it out for each individual piece, we go through and we have ways of determining what all of that is. And that becomes the body's moment of inertia. And a moment of inertia is going to be kilogram times meter squared. It's going to be a scalar. It's always positive. In other words, it doesn't have any direction, anything like that. You can think of it, it's similar to having a particle of mass. Mass doesn't have any vector components with it. Now, you start working with momentum, that's different because you're adding in velocity, but mass by itself does not. So again, we've got our formula here for I omega squared. So let's take a look at a problem here. We're going to calculate the moment of inertia of a sculpture that consists of 3 small spherical masses connected with massless rods. Yep, that sounds like modern art to me. So, of course, in order to determine the moment of inertia, we have to specify the axis of rotation. So first, we're going to find the moment of inertia about the axis passing through spheres B and C. Don't have to worry so much about A because that's what we're going to be using as the axis of rotation. So we know what the distance is here. We know what the distance is here. The distance between them is not really so much other than it just sets up a right triangle for us. So for each calculation, we find the perpendicular distance from each sphere to the axis of rotation. And then we're going to take each sphere and model it as a point. Why? Because we can get away with that. It's physics. So for the axis passing through spheres B and C, their distance from that axis is 0. So similarly, the distance of sphere A from the axis passing through it is going to be 0. So when we go through and we compute all of this, R is going to be measured from the chosen axis of rotation. For axis BC, the spheres B and C lie on the axis RB and RC, which is going to be 0. So neither contributes to the moment of inertia. So only sphere A contributes. We've got the mass here. We've got the radius here. That's the distance. And we're going to find that the moment of inertia for BC, if this were to be the this axis on which it rotates, then this would be the only thing that would contribute to it. Now, for an axis that points through point A, perpendicular to the plane of the diagram, this actually is going to be a sphere that passes through the axis of rotation there, so the radius is going to be 0. Masses are going to be the same as before, so if we put an axis here, this is going to be our computation for the moment of inertia. If it rotates about that particular axis, then we know, if we know what the angular velocity is, then we can determine what the kinetic energy is. So the moment of inertia of an object depends on the location of the axis. In other words, we just can't say, well, this is the moment of inertia. We have to refer to it with where the axis actually is. If we don't do that, then it's incomplete. We don't have enough information. Different shapes are going to have, actually the same shape is going to have different moments of inertia depending on where you put the axis of rotation. If you put it, you've got a slender rod, axis goes straight through the center, this is going to be your moment of inertia. This is computed in calculus. So take it for what it's worth. And we're not going to go through exactly how that's computed, but just take that for what it's worth. If, however, we take the axis of rotation and put it at the end of the rod, this is the value we're going to use. Let's say we've got a rectangular plate and the axis goes through the center. This is going to be your moment of inertia. If we take the plate and put the axis of rotation on one side of it, this is what it ends up being. If you've got a hollow cylinder with this as your axis, then you got your moment of inertia there. And, you can come up with all kinds of things that you never even thought of before class started today. These are the kinds of things that will come about for values for a moment of inertia. So anyway, we got a few more problems there to work through. But let's go down to potential energy for a rigid body. So we're going to want to apply the law of conservation of energy to rigid bodies. This is going to allow us to solve certain types of rigid body problems in a rather straightforward manner by keeping track of the changes in the body's kinetic and potential energy. So to do that, we're going to need to know how to calculate the potential energy of a rigid body. If you have a uniform gravitational field, gravitational potential energy of a rigid body is going to be the same as though all the masses were concentrated at the center of mass of the body. So suppose we take the y-axis vertically upward and define the potential energy to be 0 when it's on the ground. For an object with total mass, the potential energy is going to be this, where y sub cm is the vertical coordinate of the center of mass. We need to define the origin of the coordinates where this holds true. So if your body is a collection of masses and the weight of element is going to be this, mass times gravity, its potential energy is going to be this, and so the total potential energy is going to be the sum of all of that. So if we rewrite this and take all the masses out and say that everything is positioned there at the center of mass, then we can just say that the total mass is going to be the mass of all of those things, with this being all of their y coordinate, and then this becomes their potential energy. So finally, rotation about a moving axis. So when a rigid body undergoes both motion of its center of mass and rotation about an axis through the center of mass, the total kinetic energy is going to be given by this. This is linear plus rotational kinetic energy. So you can see here, you've got an object, say a baton, that's being thrown through the air and is ends up, turning itself over. How do we describe it? Well, we can describe that by taking the object and modeling it as though it were not rotating and just being thrown linearly. And we can add to that any energy that comes about when you add rotational motion. So the kinetic energy from both of those need to be added together. Ultimately, this graph is representing what I just talked about. This is the same thing here. So for the special case of an object rolling without slipping, V sub cm, the velocity of the center of mass, and omega are related to each other by this particular formula, where r is going to be the radius of the object. So we're not going to go through the derivation and just say that it looks reasonable and it can be proved rigorously. Okay, that means two things. Number one, take them at their word, or number two, I can't do it, so I'm not going to include the derivation here. It could mean number three, you're not interested, so we're just not going to put it in there, I suppose. But we're often, we'll often refer to these two terms as translational kinetic energy and rotational kinetic energy. And we're going to apply the conservation of energy to this. So let's say we've got two racing cylinders. So we've got two cylinders are released simultaneously to roll down an inclined plane. They have the same diameter and the same mass. So one cylinder is solid while the other one has a hollow cavity. Which cylinder, if either, reaches the bottom of the plane first? Well, because equal masses roll down from the same height, the decrease in gravitational potential energy is going to be the same for both cylinders because they have the same mass. This energy is converted to kinetic energy. Some of it becomes translational kinetic energy, and some becomes rotational kinetic energy. Conservation of energy gives that the gravitational potential energy that we have is going to end up being converted into translational kinetic energy and rotational kinetic energy. Because both cylinders have the same gravitational potential energy, the cylinder with the smallest rotational kinetic energy will have the largest translational kinetic energy, and therefore the larger value of this and of that. So a cylinder with the largest V is going to win the race. Because both cylinders have the same mass and the same radius, a cylinder with a smaller moment of inertia has the smaller rotational and therefore the larger translational and therefore the larger linear velocity. So the more mass an object has near the axis of rotation, the smaller the moment of inertia. Because more of the mass of the hollow cylinder has been pushed away from the axis through the center of the cylinder, the solid cylinder has a lower moment of inertia. Therefore, the correct answer is going to be A. And then you got a few more problems there that you can work through. So that is a run through of chapter 9. I hope it wasn't that boring for you, but when you start getting into rotational elements of physics, then things start to become a little bit more complicated than they have been in the past. So do you have any questions at okay. All right, no questions. All right, well, that's going to end the lecture here. You do have some problems that you can look over there, and if you have any other issues, just let me know.